Our world is just full of systems that are complex and, well, random. Think about financial markets or even how a disease spreads. We build these super powerful mathematical models to try and make sense of it all, but what happens when those models are just a little bit flawed? So today, let's dive into a simple, and I mean really simple formula that's designed to bring some serious clarity to our most chaotic systems.
And make no mistake, the stakes are incredibly high. I mean, this quote says it all, right? A tiny little miscalculation isn't just some problem for a math textbook. In the world of finance, it can literally wipe out fortunes. And in public health, it could lead to policies that affect the lives of millions of people. Precision isn't just important, it's everything.
So that brings us to the big question. These models, by their very nature, are noisy because they're trying to capture pure randomness. So how in the world do we filter out all that distracting static, the tiny errors that just keep piling up every time a computer runs a simulation, so we can actually hear the true signal underneath it all?
Well, get this. The answer isn't some super complicated 1,000-page algorithm. It's an unbelievably elegant and honestly surprisingly simple formula.
And here it is. At its very core, this formula is what you'd call a correction factor. It takes the part of an equation that represents randomness, that's the standard deviation or the Greek letter sigma, and it just multiplies it by this little factor. The whole idea is to gently, and I mean gently, dial down the numerical errors that sneak into these simulations without messing with the basic behavior of the model itself.
And to really wrap your head around this, think of it like a polarizing lens on a camera. You know how when you try to take a photo of a lake on a sunny day, the glare from the sun just washes everything out? Well, that lens filters out the glare, and suddenly you can see the clear water underneath. This formula does pretty much the exact same thing, but for math. It filters out the glare of numerical noise so we can see the true, stable behavior of the system. So, how does this incredible little lens actually work? Well, its power comes from what you could call a perfect partnership between two of the most famous numbers in all of mathematics.
On one side, you've got the golden ratio, phi. Its job is to be the stabilizer. It shows up all over nature in things that are balanced and optimized. So here, it anchors the formula and keeps things from getting too wild. Then, on the other side, you've got pi, and pi acts as the engine. Its whole purpose here is to make the correction happen and happen fast. So you see, one brings the balance, the other brings the speed. It's a perfect team. And this is where it gets really cool. See, the formula is iterative, which just means we apply it again and again in a few steps to get closer and closer to the right answer. We use the letter k to count those steps. So on our first try, when k is 1, the bottom of our little fraction is just pi to the power of 1, or about 3.14. Simple enough. But let's say the error is still a bit too big. Well, we just turn the dial, we run it again. By the time k equals 3, the bottom number isn't just 3 times bigger. No way. It's pi to the third power, which jumps all the way up to over 31. That means our correction factor just got way, way smaller.
And by the time we get to the fifth step, k equals 5, that denominator has absolutely exploded to over 300. It's this exponential growth, all driven by pi, that lets the formula just crush the error in only a few tries. In fact, for most of the real-world tests, they found a stable, accurate answer in just 3 to 5 iterations. That's it.
Now, this whole idea of using these fundamental numbers to get something done so efficiently, well, it wasn't just pulled out of thin air. It was actually inspired by the work of a true mathematical legend. The formula's creator, Jose Lourenço Claudio Junior, drew a dual inspiration from the great Srinivasa Ramanujan. First, there's the structure. Ramanujan was famous for these incredible formulas for calculating pi that got a super precise answer really fast. How? By using massive, fast-growing numbers in the denominator. This formula does the exact same thing with pi to the power of k. But the second inspiration is more philosophical. It just captures Ramanujan's whole spirit of finding these deep, elegant, and powerful solutions by combining the basic building blocks of the universe in ways no one had ever thought of before.
Okay, so the theory is beautiful, it's elegant, but does it actually work when things get messy? Let's put it through the ultimate stress test, the absolute chaos of financial markets.
So the challenge was to take this formula and apply it to something called the Heston model. It's a major benchmark for pricing financial options, and its key feature is that the volatility itself is unpredictable. This thing is notorious for breaking down during sudden market shocks, what people call black swan events.
And the results are, well, they're just stunning. Look at this. The standard uncorrected model, that first bar, it was spitting out errors between 8 and 10% when volatility spiked. That's the kind of error that leads to a catastrophic underestimation of risk. But now look at the second bar. The corrected model absolutely slashed that error down to less than 2%. This is it. This is the formula delivering stability right when you need it most.
And it doesn't just work in total chaos. They also tested it on a more standard model, the Ornstein-Uhlenbeck process, and it showed the same incredible improvement. The uncorrected model had an error around 5%. With the correction, it dropped to less than 1%. Just fantastic.
When you lay it all out like this story becomes crystal clear. It doesn't matter if it's a standard model or a high-stress financial test, you see the same thing again and again, a massive reduction in error. And it's achieved so efficiently, in just a handful of steps. The proof, as they say, is right here in the numbers.
Okay, so let's step back from the math for a second. What does all of this actually mean for the real world? Let's take a look at the bigger picture.
The applications here are huge, and they're really important. In finance, it's a powerful tool for risk managers to help avoid those multi-million-dollar mistakes we talked about earlier. But it's so much bigger than just money. Think about epidemiology. More precise models mean more reliable forecasts for how a disease might spread. That leads to better public health decisions, better planning, and it could potentially save lives.
And that really leaves us with one final thought. This formula is just a beautiful reminder of the power of simplicity. It shows us that sometimes the best way to understand our most complex, most chaotic problems isn't to throw more complexity at them, but to look for that simple, elegant solution that might just be hiding in plain sight.